Yeah, welcome back to lecture 24, partial derivatives and total differentiation. And the previous lecture, we have studied the calculus in one variable. Means there is only one independent variable up to now. But in this topic and upcoming topics, we will study calculus in several variables. Means we have more than one independent variables. Suppose you have a function z equal to fxy and z is here dependent variable. X and y are independent variable. So if we change the value of x, it will be changed. For example, if we take sine xy plus e to the power x square minus y square. As you change the value of x, your function z will be changed. As you change y, the value of function, the value of z will be changed. So here the value of z is depending on x and y. So here x and y are independent variables. So today we will study the differentiation or partial derivatives when we have more than one independent variables. So let's start. Consider the function before this topic. We have to understand what is the limit continuity and differentiability in several variables, but it is not mentioned in the syllabus of Gate, ESE and engineering mathematics. So I will try to avoid that and we will learn how to find the partial derivatives now. But for understanding of limit continuity and differentiability in two variables, I will teach you in the complex analysis module. So right now we have the definition of limit in one variable. And with the help of one variable, I try to understand the partial derivative. It's a difficult, but for now you have to adjust with this knowledge of only. But if you want to learn in more detail, you have to learn limit continuity and differentiability in several variables first. So I'm not going in the limit continuity differentiability. This topic I will cover in complex analysis module. Z equal to fxy. If the limits, see at the limits, limit delta x tending to 0, f of x plus delta x comma y minus f of xy over delta x. Remember, this look like this limit h tending to 0, f of x plus h minus fx over h. Here h is replaced with delta x and a new variable y is involved. But y is not changing here. We are changing only x, or we are doing increment in x. Increment in x only. Y is treating as constant. If this limit exists, then we say this is the partial derivative of z with respect to x. If this limit exists, then this is called partial derivative. This is the notation of partial derivative. With respect to x means del x, and of which function? Of z. So del z by del x. This is the notation. If this limit exists, means we are incrementing in the x, y is keeping as a constant, then this is called partial derivative of x. Similarly, if we do increment in y, limit delta y tending to 0 and x is keeping as constant minus fxy over delta y, then this is, if this limit exists, then this is called del z over del y. So main thing is limit must be exist. So what we understand now? If z is function of xy, I think some people represent like this: zxy means z is function of xy. Then del z by del x is given as del f by del x. We can also represent like this: limit delta x tending to 0 f or z x plus delta x comma y minus fxy over delta x. This will be equal to del z by del x if and only if this limit exists. At any point, if you find the partial derivative, suppose at any point a comma b we are going to find, then this will become limit delta x tending to 0 f of a plus delta x comma y, y means b, minus f at a comma b over delta x. Similarly, we can write for the y derivative del z over del y is a limit delta y tending to 0 f of x comma y plus delta y minus fx y over delta y. At any point a comma b, we write at any point a comma b, it will become limit delta y tending to 0 f of a comma b plus delta y minus f a b over delta y. So these are the definitions of partial derivative with respect to x and y, provided these limits are existing. Now, suppose we have some examples also. Let's see some examples. Z equal to x square plus y square plus 2x. 2x is x cube minus y cube. What will be the del z by del x? We have to differentiate only x. Y will be treated as constant. So it will be 2x plus 0 plus 6x square. What will be the del z over del y? It will be 2y minus 6y square. We have a second example, e to the power axy. Then what will be the del z over del x? It will be e to the power axy. We have to differentiate axy with respect to x. Y will be treated as constant. It will be ay only. But you can observe that I am not using limiting case here because these functions are differentiable functions and defined in the entire domain of real number. If we take x belongs to real number and y belongs to also real number, then x comma y belongs to real cross real. Means this is a ordered pair of r cross r, or some people call it as R2 also. You will learn in additional topic. I will teach you vector space, then I will tell you. The only concern when we have to apply the limit definition for obtaining the partial derivative. If you are going to find the partial derivative at any point, suppose you want derivative at 1 comma 1. At 1 comma 1, this function is defined. So you can get the partial derivative very easily. Del z by del x at 1 comma 1 will be 2 plus 6 means that will be 8. If you are going to find del z by del y at 1 comma 1, it will be minus 4. Because the given function is defined at 1 comma 1. So we can use direct differentiation, which I have studied in class 10 plus 1. And differentiating with respect to x means we are treating y as a constant, and differentiating with respect to y means we are treating x as a constant. But if function is in the form of suppose x square minus y square over x minus y, and z at 0 0 I am giving to you 0. Find del z over del x at 0. Find del z over del x at 0 0 and del z over del y at 0 0. So at 0 comma 0, this function is not defined. It is 0 by 0 form, means indeterminate form. Whenever you get indeterminate form, you always apply the limit definition. Limit definition will work in every case. But if your function is not in the indeterminate form, you can go by this method also, which I have discussed up to now. But if your function is in indeterminate form, you have to use the limit approach for finding the partial derivative. So what will be the partial derivative? So del z over del x, I told you this is limit delta x tending to 0, because you are going to find the partial derivative in the neighborhood of 0, 0. So it will be, if you are supposing this is equal to fxy, then it will be or zxy, z equal to zxy, then your derivative will be zx plus delta x comma y minus zxy over delta x. If you are going to find at 0, 0, it will become limit delta x tending to 0, z delta x comma 0 minus z0 0 over delta x. If you put x and y both 0, because we are going to find at 0, 0. So what is the limit delta x comma 0? Delta x comma 0. You have the value zxy as x square minus y square over x minus y. Then your value will be of zx minus z delta x comma 0 will be z delta x comma 0 will be if you put x delta x in place of x and y, 0 at place of y, so it will be delta x square minus 0 square over delta x minus 0. So it will be delta x only. So it will be delta x minus 0, z 0 0 is given to 0 upon delta x, so it will become 1. So the partial derivative of z with respect to x at 0, 0 will be 1. Similarly, you can find the partial derivative of z with respect to y also using this definition approach. So when we will apply the definition, when at the given point the function is in the indeterminate form. Let's see what are the higher order partial derivatives. Higher order partial derivatives. These derivatives can be also found using the limit approach, but with the one limit you can solve these also. So let z equal to zxy or fxy, you can use any notation, be a function. I am discussing here for only 2 variables. It can be generalized for n variables also. Function of 2 variables and its first order partial derivatives. What are the first order partial derivatives? That was del z over del x and del z over del y exists at all points. Important is at all points in given domain, whichever domain is given. Then its the second derivative del z over del x square can be written as del over del x, del z over del x. It will be again a function of xy, and that we can assume some z1 xy function, and it can be differentiate with respect to x. Again, we will get the second derivative of z. And what about del z? Del 2z over del y square, that is second derivative of z with respect to y. These are called second order derivative. In the second order derivatives, we have 2 mixed derivative also. Suppose you are going to find del z, del 2z over del x, del y. Means, what is the meaning of this? This is the derivative of del z over del y with respect to x again. And similarly, if we write del 2z over del y del x, this is the derivative of del z over del x with respect to y again. We have to tackle first this one, then second this. This is the first calculation will be del z over del y, then second calculation will be del by del x. Here first calculation will be del z by del x, second calculation will be del z over del y. So these are called mixed derivatives. So what are the notations? Notations are very important here. Notations I am telling you. If you have del z over del x, this is called zx with respect to x. Del z over del y, this is called zy. Del 2z over del x square, second derivative is zxx. Del 2z over del y square is zyy. And del 2z over del x del y is called zxy. We start from this side. Means firstly differentiate with respect to y, then differentiate with respect to x. Del 2z over del y del x, this is called zyx. We start from left side. So it's a derivative of del z by del x with respect to y. So these are two mixed derivatives. Let's see some important remarks. First, is mixed derivatives are equal? Is mixed derivatives are equal? No. Not in general. So when these mixed derivatives are equal, if zxy and zyx are continuous at a point, then at a point, suppose the point is xy, then zxy equal to del yx, zxyx. Means if these two are continuous at any point, then that point these will be equal. Suppose these are equal at a comma b, continuous at a comma b. It means zxy at a comma b will be equal to zyx at a comma b. So the continuity of these two is compulsory. What is the meaning of continuity here? If you differentiate it with respect to y, then with respect to x, you will get again a function of xy which must be continuous at the given point. How to check the continuity? That is a topic for you. You try to finish it from any good book. You can take Jan and Anger book, or I will discuss in complex analysis also. We have some other important points. So when these are equal, if these are continuous at a given point, then these two will be equal. This is an important point for gate question. Second point I have, some people confuse del 2z over del x square is not del z over del x whole square. Remember this point. This is not equal to del z over del x square. Or del 2z over del y square is not equal to del z over del y square in general. Third, this is not correct notation. If you have del by del x plus del by del y whole square and you are operating z after that, then what will be the formula? So if we use a square plus b square, it will be del 2 over del x square plus del 2 over del y square plus 2 del 2 over del x del y. Now if you apply the z, you will get del 2z over del x square plus del 2z over del y square plus 2 del 2z over del x del y. These remarks will help in the Taylor series expansion of a function which have two independent variables. If you have del z over del x plus del z over del y whole square, both are distinct, remember here, then this is equal to del z over del x whole square plus del z over del y whole square plus 2 into del z over del x into del z over del y. Del z over del y. So these are some important points. Let's see some more example. If z equal to tan inverse y by x. And x and y both are not 0. Means we are excluding 0, 0 from the domain of R cross R. Then verify mixed derivative is equal for all other points. We can see that this function is not defined at 0, 0, so it will not be continuous at 0, 0. That's why we cannot find the mixed derivative at 0, 0, and that will not be equal. But for other point, the mixed derivative will be equal. So you can verify that. Let's see the solution. Z equal to tan inverse y over x. Firstly, I am going to find the first order derivative. So del z by del x, we can directly find derivative because this function is defined for other point. If 0, 0 is not excluded, then we have to use the limit approach. But 0, 0 is already excluded. It means now the function is defined in the given domain, so we can apply the direct differentiation formula. So the derivative of tan is 1 plus y over x whole square, and derivative of y over x with respect to x will be minus y over x square. It is disturbing at 0, 0, but we have already excluded that point, so I can use this. This will be equal to minus y over x square plus y square. What about del z over del y? This will be equal to 1 over 1 plus y over x whole square into derivative of y by x with respect to y will be 1 over x. It will be x over x square plus y square. Now we will find del 2z over del x del y. This is nothing else. It is del by del x of del z over del y. Means this is equal to del by del x of x over x square plus y square. So we have to differentiate it with respect to x again. So denominator whole square, we can differentiate it because it is disturbing at origin only, and origin already we have excluded. X square plus y square, and derivative of x is 1 minus x into x square plus y square, derivative with respect to x will be this. So it will be y square minus x square over x square plus y square whole square. Similarly, you can check that del 2z over del y del x is equal to y square minus x square over x square plus y square whole square. So these two are equal. For partial derivatives, Euler give a very beautiful result, and that result is valid for homogeneous function. For homogeneous function, they give some smart calculation. Let's see what is homogeneous function and what is Euler theorem for the homogeneous function based on partial derivatives. Homogeneous function. A function fxy or zxy is depend what notation you are following. It's said to be homogeneous function of degree n in x and y. This definition can be generalized for n variables also. I am giving for 2 variables only. If it can be written in any one of the following forms. First form is f of lambda x comma lambda y is equal to lambda to the power n x comma fx comma y, where n is called degree for any non-zero scalar lambda. Lambda is not equal to 0 here. Second is, if lambda is 0, then you will get f0 0 equal to f0 0. That is true also, I think. But we are checking degree for lambda not equal to 0. Or fxy can be written as x to the power n g of y over x. If from the given function we can separate the x to the power n, and the remaining function can be written as y by x form, then it is a homogeneous function of degree n. Or fxy can be written as y to the power n g of x over y. I'm not writing this point because for lambda equal to 0, it will be f0 equal to f00. That is true, I think. For m variables, we can generalize the result. Suppose z equal to f of x1, x2, xm, then this is called homogeneous function of degree n if it can be written as f of lambda x1, lambda x2, lambda xm is equal to lambda to the power n f of x1, x2 and so on xm. So this is the definition of homogeneous function. So let's see some examples for homogeneous function. Let we have some function fxy. Check homogeneous or not. If homogeneous, find degree, find n degree. Suppose you have a function x square plus xy. If we take the function x square plus xy, we have two approaches. What are the two approaches? We can write like this: f of lambda x, lambda y will be lambda x whole square plus lambda x into lambda y. We can see that lambda is perfectly out with the power 2. Lambda square x square plus xy. This is again equal to lambda square of xy. So f of lambda x, lambda y is written as lambda square of xy. So its degree is 2. What is the another way to write it? We can write like this: if we take x square common, then it will be 1 plus y over x. This is the function of y over x. So it can be written as g of y over x. So this is a homogeneous function of degree 2. But I will advise you, you follow this definition. This is a better way to find the degree. It will confuse sometimes. If we check for tan inverse y over x, then if you let f of lambda x, lambda y, you have fxy as tan inverse y over x, then f of lambda x, lambda y will be tan inverse lambda y over lambda x. So lambda is cancelled out. It is again tan inverse y by x. So we can write lambda to the power 0 in the multiply. So it is lambda to the power 0 fxy. Means this is also homogeneous function with degree 0. With degree 0. If we have the function like 1 over x to the power 4 plus y to the power 4 plus z to the power 4, we can check for 3 functions also. So fx, y, z I am taking as 1 over x to the power 4 plus y to the power 4 plus z to the power 4. If you find f of lambda x, lambda y, lambda z, it will become 1 over lambda to the power 4. You can take outside x to the power 4, y to the power 4 and z to the power 4. If you put lambda x, lambda y, lambda z in the place of x, y, z, you will get this type of equation only. So lambda to the power minus 4 fx, y, z. It means you can write in the form of lambda to the power n fx, y, z. So degree is minus 4 here. So these all are the homogeneous functions. Let's check for one more function. Check for fxy is equal to x plus y square over x square plus y. It is homogeneous or not? If we write f of lambda x, lambda y, it will be lambda x plus lambda y whole square over lambda x whole square plus lambda y. We can see that we cannot take common from the lambda because we have lambda, then it is x plus lambda y. Lambda is inside also. We cannot take separately or perfectly outside. So this is not a homogeneous function. This is not a homogeneous function. Now if we check for another example, fxy equal to under root x over under root x square plus y square. You can check f of lambda x comma lambda y is equal to under root lambda x over under root lambda x whole square plus lambda y whole square. Now this is equal to lambda to the power 1 by 2 under root x. We can take lambda outside from under root because lambda square can be taken outside, then under root of lambda square will be lambda. It will be lambda to the power minus 1 by 2 fxy only. This is again fxy. It means this we can take lambda perfectly outside, and the degree of this homogeneous function is minus 1 by. This is a homogeneous function. Now let's see what is the Euler's theorem for the homogeneous function. This is very useful result in the theory of partial derivatives. If fxy is a homogeneous is important, homogeneous function of degree n in x and y, and h continuous first and second order partial derivatives. This is a very important line. For the Euler's theorem statement, continuity of first and second order partial derivative is required. It is not given in many local books, but this is a required condition. Then only mixed derivative will be equal. Second order partial derivative then we have two results. X into del f over del x plus y into del f by del y is equal to n into f. Or if you write z equal to fxy, then it can be written as x del z over del x plus y del z over del y equal to n into z. Whichever notation you follow, you can write. And the B result is x square del 2f over del x square plus 2xy del 2f over del x del y, or del y del x you can write, because we are taking here continuous second order derivative. It means mixed derivative will be equal over here. Plus y square del 2z del 2f over del y square is equal to n into n minus 1f, where n is the degree of homogeneous function. Or you can write x square del 2z over del x square plus 2xy del 2z over del x del y plus y square del 2z over del y square equal to n into n minus 1z. So these are the statements of Euler's theorem. I'm going to prove first part. Second, you can try by yourself only. It will give you idea actually. Let's see the proof. I'm going to first part. I'm going to prove x del z by del x plus y del z by del y equal to n into z. Here I'm taking z equal to fxy is a homogeneous function of degree n. So I told you if fxy is a homogeneous function, we can write in the form of x to the power n g of y by x, or y to the power n g of x by y in that case, because we are taking x to the power n entire x common, then x will be in denominator in the remaining term, and the highest power will be take common in y, then y will be in the denominator of g function. So this is also a form of homogeneous function of degree n. I have already told you. Then what will be that? This is equal to z only. So what will be the del z by del x? This is equal to z only. We have x in two places, so we have to use multiplication rule. First is outside. Derivative of z, I am taking g dash y by x, and differentiate with respect to y by x with respect to x will get you minus y over x square plus g of y by x in the derivative of x to the power n with respect to x will be nx to the power n minus. Now we want in the LHS x into del z by del x. So we multiply x both the side. You will get minus y into x to the power n minus 1 g dash y by x plus n into x to the power n g of y by x. Here, one power will be cancelled out and one power will be subtracted from here if you multiply. Now you find del z over del y. With respect to y, x to the power n will be treated as constant. Derivative of g will be g dash y by x, and derivative of y by x with respect to y will be 1 by x. Now if you multiply y both the side, y del z by del y will be y into x to the power n minus 1 g dash y by x. This is the equation number 2. If you add 1 and 2, you can see that x del z by del x plus y del z over del y is equal to, these two terms are cancelled out here. This term and this term are going to be cancelled out. It will give you n into x to the power n g of y by x. This is already, I have assumed that f or z. So this is equal to nz. So this is the proof of first result. Similarly, you can prove second result. Let's see some examples based on Euler theorem. If z equal to x square tan inverse y by x minus y square tan inverse x over y, and x and y I am taking both are positive. Both are positive. In the mixed derivative condition, you discuss this problem. Yeah, remember here also x and y are positive. Remember here x and y both are positive here. Because if x is positive, y is negative, then this tan inverse function will not be continuous. Because one limit will go plus pi and another limit will go if x is greater than 0 and y is tending to 0 from approaching a 0 by 0 form is not being defined here. As if you are checking the continuity at 0, 0, if both are not positive, then at x axis from the right you will get tan inverse 0, it will be 0. And from the tan inverse infinity will go to pi by 2. If you go on the axis, and another axis will go to 3 pi by 2. Similarly, one axis will go to 0 and another will go to pi. If you are going in the left neighborhood and right neighborhood of origin. That's why we are excluding origin and we are taking on the first quadrant. Because on the axis the function will not be continuous. I will discuss this problem for the logarithmic function in the complex analysis module. Why I am taking this domain. Now if you see, suppose this is your fxy. This is your fxy. Check the homogeneous. We will check the test f of lambda x lambda y is equal to, replace x by lambda x square tan inverse lambda y over lambda x minus lambda y square tan inverse lambda x over lambda y. So here it will be lambda square x square tan inverse y by x minus lambda square y square tan inverse x by y. We can see that lambda square is perfectly outside x square tan inverse y by x minus y square tan inverse x by y. Or it can be written as lambda square into fxy. So it is a homogeneous function with degree 2. Then the asked result in the problem is, what is x del z by del x plus y del z by del y? It will be equal to nz, yeah, it means 2z. And if you are going to find x square del 2z over del x square plus 2xy del 2z over del y square plus y square del 2z over del y square, that is equal to n minus 1 into z. It will be equal to 2 into 1 into z. It will be again z. So these two problems are very easy using Euler's theorem if the given function is homogeneous. Similar, I have one more example. If z equal to x cube plus y cube over x plus y, I am not taking x and y origin here, not 0, 0. It means continuous everywhere now. We have to find what is x del z over del x plus y del z over del y. No need to calculate, just check fxy. It is homogeneous or not. If it is homogeneous, then apply Euler's theorem. So f of xy is given to you x cube plus y cube over x plus y. So f of lambda x comma lambda y can be written as lambda x cube plus lambda y cube over lambda x plus lambda y. So f of lambda x comma lambda y will become lambda cube x cube plus y cube over lambda x plus y. So lambda square is perfectly outside and remaining function is fxy. It means this is again a homogeneous function with degree 2. So it is equal to nz. Now it will be 2z only. We have some remarks also. One of the most important remark I am going to discuss here. If z equal to or u equal to some function f inverse gxy is not homogeneous function, but if you take a f this side, a fu equal to gxy, this function is homogeneous function. This complete function is not homogeneous, but the inside function is homogeneous. Is homogeneous function of degree n, then we have very important results. Let us assume as z. Then x del u by del x, but we are interested in del u by del x, plus y del u by del y is equal to n into fu over f dash u. Fu over f dash u. F dash is representing here the derivative of fu with respect to u. Call it as gu. Let call it as gu. Or hu. I am calling as hu now. Calling as hu because g already I have assumed there. And what about the second order result? X square del 2u over del x square plus 2xy del 2u over del x del y plus y square del 2u over del y square is equal to hu h dash u minus 1. What is hu here? Hu is n into fu over f dash u. When the inside function is homogeneous but entire function is not homogeneous, then by taking inverse, if the entire function become homogeneous, we can apply this result. Let's see one example. Suppose you have u equals to log x cube plus y cube over x plus y. And I am taking here x and y both are positive. Find x del u by del x plus y del u by del y and x square del 2u by del x square plus 2xy del 2u over del x del y plus y square del 2u over del y square. If we see, suppose this is your function capital Fxy. Let's check homogeneous. This is or not. Let capital Fx is log x cube plus y cube over x plus y. Then f of lambda x comma lambda y is log lambda square x cube plus y cube over x plus y. You can check that. One lambda will be considered. Lambda square is not perfectly outside. So we can say that this function is not homogeneous. But if you see, for the entire inside function lambda square is outside. It means the inside function x cube plus y cube over x plus y is a homogeneous function. So what we have to do? We have to take the inverse both the side. So if we take log this side, it will become e to the power u equal to x cube plus y cube over x plus y. If you assume this function as gxy, and find g lambda x comma lambda y, it will be homogeneous function of degree 2. You can see that. It means if we assume this is equal to fu, then x del u over del x plus y del u by del y will be n into fu over f dash u. So what is n is? N is 2 here, degree is 2. Fu is e to the power u. What is the derivative of e to the power u? It will be e to the power u only. So the value of this will be 2. And what is the value of this? I have already told you this is equal to hu. If we assume hu, then it is equal to hu h dash u minus 1. So hu is 2. What is the derivative of 2 is 0. 0 minus 1 is equal to minus 2. This value is minus 2. Let's see one more example based on this. If you have z equal to or u equal to tan inverse x cube plus y cube over x minus y, and x and y both are taking a positive here, are not equal to 0, 0. Because I'm taking positive only, then only it will be better. So what will happen here? If you see, it will, if we assume this is a capital fxy function, tan inverse x cube plus y cube over x minus y. Now if you check f of lambda x comma lambda y, it will be tan inverse lambda x cube plus lambda y cube over lambda x minus lambda y. So it will be tan inverse lambda square x cube plus y cube over x minus y. So lambda square is not outside. It means this function is not homogeneous. But here we can see that for the inside function, lambda is outside. So by taking the inverse, it means tan u is equal to x cube plus y cube over x minus y. This is your gxy now, and this is your fu now. So gxy is equal to x cube plus y cube over x minus y is homogeneous of degree 2. You can verify that. I have already verified inside here. So now what will be the x del u by del x plus y del u by del y? It will be n into fu over su. So it will be 2 into fu is tan u, and derivative of tan u is sec square u. If you simplify it, you will get 2 sin u cos u, which means sin 2u. What about the mixed derivative, second derivative result? You can find the second derivative result here. I am going to solve here. For the second derivative, your hu will be sin 2u now, and for sin 2u, h dash u you have to find. So second derivative will be x square del 2u over del x square plus 2xy del 2u over del x del y plus y square del 2u over del y square is equal to hu h dash u minus 1. This is your hu now. So it will be sin 2u, and derivative of sin 2u is 2 cos 2u minus 1. So this is the second derivative. So by the help of Euler's theorem, you can find it. We can apply Euler theorem on fu now, because fu is homogeneous now. We cannot apply Euler's theorem on u now, because u is not homogeneous function, but fu is homogeneous. So remember here, this is not homogeneous, but by taking the inverse, the new function fu is homogeneous, so we can apply the Euler's theorem because that is valid for homogeneous functions. We have one more remark. Let f equal to f1 plus minus f2. f1 is homogeneous function of degree n1, and f2 N2 is homogeneous function of degree N2, and N1 and N2 are not same, and N1 and N2 are not same, but we can apply the homogeneous condition or Euler's theorem on F1 and F2 both, because both are homogeneous function. So what will be the x del f by del x plus y del f by del y? It will be x del by del x of f1 plus minus f2 plus y del over del y f1 plus minus f2. Now you separate f1 functions. X del f1 by del x plus y del f1 by del y plus minus x del f2 by del x plus del y del f2 by del y. So this is a homogeneous function of degree n1, so it is equal to n1 f1, it is equal to n2 f2. So this is the result, n1 f1 plus minus n2 f2. When we have a linear combination of two homogeneous functions, we can find this result for the combined function also. So I'm going to end here. In the next lecture, we will study the total differentiation and Jacobians. Okay, thank you.